What is a geodetic datum? As mentioned in previous sessions, a geodetic datum is, again, just a set of constants. So in the horizontal datum, I talked about the orientation of the datum, the location of the monument, the size and shape of the Earth. Well, the size and shape of the Earth don't really apply directly into the definition, particularly in the classical definition of a vertical datum. But having an origin is very, very important. That's an important part of any datum. And a name, again, very much like the horizontal. So in the case of vertical datums in the United States, we have a number of them. I'm just giving you one example here in this slide, which says National Geodetic Vertical Datum of 1929. So it tells you it's a vertical datum and it tells you the time frame. And just like the horizontal datum, it's defined by some set of survey monuments, somewhere in which you can go and access accurate heights so that you can produce new heights, whether you're going to do it through leveling or you're going to do it through GNSS observations. So let's take a look at the two specific types of geodetic datums as it relates to this, and the geodetic control that's associated with it. So remember, when you have the geodetic control and somebody quotes you some particular accuracy statement, oh, it's a first order benchmark or it's a third order benchmark, that those are national standards, and there are documents out there that you can go and access that tell you exactly what a first order benchmark is versus a third order benchmark. And then somebody has to go through the process of evaluating that. Do these marks, do the data associated with, do they actually meet that accuracy standard? And somebody adjusting and tying them together. This is one of the very common faults that has often been the problem with local vertical reference frames in parts of the United States and certainly around the world, is that an entity will come in and create a realization of the vertical datum. Now, it might have been the Coast and Geodetic Survey. They would come in and provide some primary leveling, and then perhaps the local community would then follow up to that and provide their own densification of that vertical datum. And what I've often found is those densification programs, while they may have been done very, very well early on, over time, as monuments get disturbed or destroyed, they're put together, they're replaced or they're maintained piecemeal with different types of procedures. Not everything is consistent, so over a period of, in some cases, not more than just a few years, you start to find that individual monuments will no longer fit together, in addition to the fact that marks can be disturbed or destroyed by natural forces such as subsidence or uplift. And then finally, the documentation, the data that's provided. If you're going to put the geodetic control out there, there must be some form of documentation so that the user knows where the data come from. How good is it really? So the two types of vertical datums, obviously you can have a relative datum to anything that you want. You can go put a nail or a railroad spike in a utility pole, call it 100 feet, and off you go. But we're in the process here of talking about geodetic datums and the national reference frame. And there are two types. And sometimes they're confused with one another. If you live in the coastal environment, which a significant portion of the country does, you have tidal datums. Right? And these are specific, defined vertical height systems that define various locations of the tide in a specific area. And one of the most common ones that people refer to, and often erroneously, is mean sea level. And we hear this all the time. Oh, the height of this point is X number of feet or meters above or below mean sea level. Well, mean sea level, like the other acronyms that you see here, mean lower low water, mean low water, mean high water, mean higher high water, which are just a few of the defined tidal datums, are very specific and very localized. That is, a tidal datum A only exists at or near the shoreline. So for example, you cannot have mean sea level in Des Moines, Iowa. Maybe 40 million years ago you did, maybe 40 million years in the future you will. But today there's no mean sea level in Des Moines, Iowa. Right? You have to be relatively close, typically within a couple of miles of the shoreline. And because of the nature of tides, the fact that there are different types of tides, and the tidal regime changes, in some cases, quite dramatically from one place to the next, tidal datums can be very, very localized. And so mean sea level, for example, in Annapolis, Maryland, is not the same level surface as mean sea level in New York, or in Jacksonville, Florida, or in San Diego or Seattle. So tidal datums are purely local. Now, I'm not going to get into great depth on tidal datums. I want to introduce them as a critical part of the national infrastructure. And I've got a couple of slides here that just highlight the importance of those vertical datums. But for those of you who may be watching this program and you're interested in more information on tidal datums, I would highly recommend that you go to the website that's linked here, Tides and Currents at NOAA.gov, because tidal datums are defined by an office that's part of NOAA, the National Oceanic and Atmospheric Administration, known as the Center for Operational Oceanographic Products and Services, or COOPS. So they are the ones who are responsible for our National Tidal Datum Epic. So I give you their link. Now, the main part of this presentation on vertical datums is about the geodetic side. And a geodetic datum here is differing from the tidal datum, even though they might be closely connected, in that a geodetic datum provides a foundation, hopefully provides a solid foundation for a larger area. So if I want to have a consistent height system, for example, from Maine to California, that's a geodetic datum. Even though there are going to be differences in tidal datums, the tidal regime on the East Coast and the West Coast and the Gulf, I want to have a consistent height system from one end of the country to the other. And the idea there is I'm going to connect it to those tidal datums. I'm going to use some of the same benchmarks and very likely some of the same data, but they're going to be smoothed out over the entire continent, not defined specifically at any one specific benchmark saying, okay, everything now is mean sea level. That just does not occur. If you lived on a small island, like Guam, maybe you can get away with that, but we don't. So various types of tidal datums or definitions that you'll see for the United States. The National Geodetic Vertical Datum of 1929, which is the previous vertical datum. The North American Vertical Datum of 1988, the current national datum for the conterminous United States and Alaska. IGLD, the International Great Lakes Datum for surveyors and engineers who work in and up around the Great Lakes. That's an important datum. So there are a number of them, the various island areas of the United States, Puerto Rico and the Virgin Islands, Hawaii, American Samoa, Guam, all have their own localized vertical datums. So just to highlight elements of tidal datums so that you've got some information to work with should you have interest in them. This should just give you an idea of the range of these types of tidal datums. Many of them have their own specific definitions and they have their own specific purposes. So for example, nautical charting in the United States is defined based on mean low or low water. But navigation, building bridges or other structures over navigable waterways, you want to have related to mean high water. So ships can pass easily underneath. So it's important to understand the differences in these tidal datums. In addition, many of the tidal datums have definitions relative to boundary issues. And we're not going to get into that specifically today, but I've just highlighted a few here that the various ranges and uses of the local tidal datums as they pertain to shoreline infrastructure of the United States. So, okay. Talking about vertical datums, you have to first start talking about heights, different types of heights. And while there are a number of different types, we're only going to talk about the three most common. We're going to talk about orthometric heights, geoid heights, ellipsoid heights. Now I've got the definitions here. So let's take a look first of all at the orthometric heights, what many people commonly but erroneously refer to as mean sea level. These are heights relative to the national vertical datum, which in this case is the North American Vertical Datum of 1988. And it's simply as it says. It's the distance from the geoid, the surface for which the system is defined, along the plumb line. And how accurately can we do that? Well, we can determine heights, relative height differences, orthometric height differences, easily to sub-millimeter level. You'll see some pictures in a little bit. Digital barcode levels, probably the finest surveying instrument that's ever been made. It's quite, I shouldn't say it's easy to do that, but it's not a lot of hard work to get sub-millimeter differences from one mark to the next. A couple of centimeters, very, very easy to achieve with leveling observations. Geoid heights, geoid separations, the distance between the reference ellipse. I remember in the previous session on geodetic surfaces, I talked about the reference ellipsoids. In the session on horizontal datums, I talked about the reference ellipsoid and its importance to the geodetic reference field. So the geoid height is the difference between those two at any given point. And how well do we know what that is? Well, that's one of the big issues. Right now, from the current national models that are produced by the National Geodetic Survey, it ranges, again, at the 95% confidence level, somewhere in the range of 2 to at least 4 centimeters. So we've gone from 1/10 of a millimeter, or maybe 1 or 2 millimeters, already into the range of a couple of centimeters. Now, if I'm going to use GNSS to provide heights, I have to know how good the geoid height is, the geoid model is, that's being used in my computation. So a couple of centimeters, easily 3 to 4, maybe even as much as 5 centimeters. It depends upon how good the model is, and the model is dependent upon the amount of data that's been collected. Now, by the end of this presentation, I'll have shown you what NGS tries to do there. The other height is referred to as the ellipsoid height, and this is the height that comes directly from a GNSS observation. Right, so GPS, GNSS is a three-dimensional coordinate system, latitude, longitude, and ellipsoid height. Right? But that ellipsoid height has nothing to do with the Earth's gravity field. Water does not necessarily run downhill in ellipsoid heights. So if I'm going to use GPS, GNSS to capture information about heights, I'm starting off with an ellipsoid height. That's going to be the primary data element that I'm going to acquire. And then I have to apply to it the geoid model, that is the difference between the ellipse and the geoid, to hopefully get a good quality orthometric height. And how good is an ellipsoid height? Well, again, it can vary. It will depend upon a number of things. A, the conditions under which you make your GNSS measurements. Hopefully if you're in a good open environment, you've got nice clean horizon, you've got lots of satellites, you're going to be there for hopefully a little bit of time, you're going to collect a lot of high quality data, and then when you process the data, getting good ellipsoid heights, making sure that you're acquiring at the very minimum the rapid orbits that are provided by the IGS and NGS. So realizing that when you begin a GPS survey, in most cases you're dealing with broadcast orbits, and they're okay, but they're not the best heights. You're going to get better heights when you get the rapid orbits. And then of course you get the absolute best heights if you wait a couple of weeks and get the precise orbits, but in the vast majority of cases today, you don't have to worry about that so much. So in most cases, the quality of the ellipsoid height that you're going to be able to achieve, again, dependent on a variety of conditions, is going to be somewhere in the range of 1 to 5 centimeters, 95% confidence. Remember, that's important. So if my requirement is a height to no worse than 1 centimeter, can I get it with GNSS? Well, let's look at the numbers. How well can I determine my ellipsoid height? Maybe 2 centimeters? Well, right there, I'm already a centimeter over. And then how good is the geoid model in whatever community you're working in? So it's important to know there how well that model is defined by the National Geodetic Survey. And in very, very few places right now, it is nowhere near 1 centimeter, 2 centimeters at best in some places. So understand that there is height types and the accuracy to which each one of them can easily be determined. So let's take a look at how accurately can we determine different types of heights. So if I really have to have the highest level of height integrity, that can only come from leveling. And you can fairly easily achieve millimeter height differences with leveling. But as you see from the slide that I have here, it's very expensive. It is in fact very time consuming, and it requires highly trained personnel. So you've got to have people who are dedicated to this process. It is not, on some occasions I've had surveyors refer to geodetic leveling as construction leveling done slower. Well, it's not like that at all. It requires a fairly significant investment in the technology. You'll see some pictures in a few minutes. But more importantly, I think, it's the trained people, the people that really can make this a productive process for you. But I don't care how you do it. I don't care how well the people are trained. Determining those height differences is still going to be expensive and time consuming. But if you must have those highest levels, that's what you're really left with. If you can live with a couple of centimeters, a tenth of a foot or so, GNSS is a perfectly usable tool. And as it says, it's way quicker, vastly cheaper, and you don't need terribly well-trained personnel to go out and capture this kind of positional information. So the user has to be well assured of what is it that they require. Just as an example, and I'm sure if those of you who are surveyors that might be watching this have certainly run into the occasion where you're talking to somebody and you'll say, well, how accurate do you need that? And the comment will almost always come back, well, I need it as accurate as possible. Well, okay, I can give you the best accuracy, but it's going to cost a fair amount of money versus a couple of centimeters. So knowing what you need is one part of it, so that you can decide which type of technology you use to deliver that data element to the client. Or as a user, as you're acquiring this information from some other source, if you have needs and you're saying, I'm capturing this data from some source that's giving it to me, what did they do? How well did they acquire that? Because remember, as I mentioned previously, and I'm going to certainly mention it again any number of times, the number of digits to the right of the decimal point have nothing to do with the integrity of the data. So a height shown to 4 decimal places done with GPS does not mean it's really that good. You need to know a lot more about it. So just as, a highlight, I love the pictures of people out doing leveling. If you took the session previously on the horizontal datums, you saw the various pictures about building towers and the different instruments that were used, and using astronomic observations as well as terrestrial observations. Well, to one extent or another, the process of leveling has not changed in well over 150 years. It is still a terrestrial measurement system that has limited sight differential. And particularly in geodetic leveling, about the farthest you can go is going to be about 50 meters. So you can't make observations 100 meters or 200 or 300 meters. But the process of leveling, as you see from the pictures here, pretty much looks the same today as it did back in the 1920s or 30s. Here you see the pictures of the coast surveyors out with the old optical level, actually a Fisher level, and you've got 2 rodmen out. Well, the same process is true today, although increasingly we're seeing the use of digital leveling so that the observer themselves do not have to read the rods. The instrument is reading the rod. And in my personal opinion, the high-quality digital barcode levels that are produced by a number of manufacturers today are the finest surveying instruments that have ever been made. If they're taken care of, they are just the best. And they can produce quite phenomenal results. But again, they're expensive and they have limited uses. So for example, first order leveling or even second order class 1 leveling, you have to have single piece rods. So a couple of meter single piece rod, first A, is expensive, it's got to be calibrated, and you might get a sense it's kind of hard to move around. You can't just fold it up and put it in the back of the truck. So geodetic leveling is the best way to go about this, but again, to highlight, very time consuming, very expensive. And no matter how well you do the leveling, you're still constrained by a number of different factors that are regrettably not terribly well known at this time. And that deals with the gravity surface of the Earth. And remember, we're not talking about the whole Earth. We're talking about the local environment that you're working in. How gravity changes from place to place because of the underlying differences in the geological structure. The direction of gravity will change and the velocity will change. So what occurs is we have a series of what are commonly referred to as equal potential surfaces. And they're referred to as level surfaces, meaning that if I have an equal potential surface, I define some surface, water does not flow along that surface. So here's an example. We have selected this dotted blue line. And this dotted blue line here is referred to as the geoid. We might also be thinking of it as the surface that defines our vertical datum, in this case, the North American vertical datum of 1988. And that is defined as the height of a specific benchmark at the mouth of the St. Lawrence Seaway up in Canada. So that benchmark, if we think about it, that benchmark is that blue dot right there, okay? And now if we extend it through the surface of the continent, that surface, again, moves a bit due to the changing nature of the gravity field below it. And you have this multitude of equal potential surfaces. So I have one right here. I have an equal potential surface right here. And if I raise my finger 2 millimeters, I have another one, and then another, and another, and another, or go down. It doesn't make any difference. Go up, down. You have multitudes of these equal potential surfaces. Fortunately, in this small environment, they're parallel. They're parallel, so I can kind of ignore that problem. But when I start running levels, particularly over areas in which the gravity field changes, and a good example of that can be coming across the United States, eastern Colorado, for example. And all of a sudden you have the big open plains, and then you run right into the mountains. You know the gravity field is changing there. Well, what happens in those environments is now these equal potential surfaces are no longer parallel to one another. And without a really good idea of what the gravity field is doing under each and every one of your measurements, you end up with a series of measurements that are not giving you what you want, which is a direct line from your surface that you've defined, in this case, the defining surface of NAVD 88, to the point in question. What you actually have is this curved surface that is perpendicular to each one of the equal potential surfaces that are involved there. So it's actually a curved line. It's not a straight line. It's a little hard to see. I've obviously taken liberties with this sketch, but nonetheless, it is a critical part of understanding the process of not observing leveling, not observing it, but processing it. And it's one of the issues that geodetic institutions around the world have dealt with, tried to deal with, for many, many years. And it's been hard because acquiring that gravity data has been so very difficult and expensive, and particularly challenging in areas that are very rugged, very mountainous. So it's only been the last 7 or 8 years that technologies have become available to us that will allow us to improve on that. And in part, that's what we're going to talk about in another session dealing with new datums for the United States. So let's highlight this again with another sketch, and hopefully this will kind of bring it together. So what I'm trying to show here, all these equal potential surfaces, and notice that they are not parallel, right? But here's my reference surface. In this case, it's calling it the surface of the geoid. You can think of it as the surface of NAVD88. And I have 2 points, A and C, that are on the same equal potential surface, meaning the height difference between that water does not flow between the two of them. Right? And what I'm going to do is I'm going to run up and over this mountain or hill. And something's going on here. The gravity field is changing in there. So these equal potential surfaces are no longer parallel. So as I level up to the top of the hill to B, I get a height difference, and then I level back down. And the height difference from A to B turns out to be identical to the height difference from B to C. But the height difference, but A and B are not identical because the equal potential surface on which they both are defined is different than the reference surface. Again, because of these equal potential, the changes in these equal potential surfaces. Now, most surveyors will not encounter this in local surveys that they're involved in. But if you're trying to run up a mountain or you happen to live in areas where the gravity field is changing rapidly, and we have many, many areas like that in the United States, this can be a significant issue if you're going long range and you need high quality heights. Again, generally not a problem if you're going just a few kilometers or so. But it's one of the bigger issues. In fact, a little bit later on I'll talk about what we discussed at the National Geodetic Survey for improving the vertical datum for the future and how we had to ultimately deal with that particular concept. So let's bring this together into a picture that includes the reference ellipse. Remember I talked about ellipsoid heights. That's the native height that you're going to acquire when performing any GNSS observations. Remember, it's a three-dimensional tool, latitude, longitude, and ellipsoid height. Those ellipsoid heights are referenced to this mathematical surface for the size and shape of the Earth, and they have nothing to do with the Earth's gravity field. So again, water does not necessarily run downhill in GPS heights, ellipsoid heights. So if I want to acquire good orthometric heights, then I need to know the relationship of the ellipse and the geoid. So let's back up from that for a moment. Again, and this is important to remember because it's commonly misconstrued by a lot of users that the geoid is the surface of the vertical datum. In the future, that will be true. That is not true today. So that's why I have in my slide here average mean sea level, which is the geoid, or the surface of NAVD88, because I just don't want to make another surface in there. So in this particular case, since we are not dealing with the geoid, we are dealing with NAVD88, and that is our national vertical datum for the conterminous U.S. and Alaska. This is the surface that defines NAVD88. So how do I model that? How do I determine what these heights are going to be? Well, here's a fairly simple case, I hope. The point where you see my little GPS receiver here, I'm going to call that an existing benchmark. It is a point that has a known NAVD88 height, an orthometric height. It has been leveled to. It is part of the National Vertical Datum. It is NAVD88. It's published by the National Geodetic Survey. Now you go out to that point, you take your GNSS receiver and you set up over that benchmark and you acquire some data and you process it. And there are a number of ways you could be doing that. You could send it to NGS and use their online positioning user surface, or maybe you're using a real-time network, or you've set up an RTK base station. there are any number of ways in which you can pursue this, and this series of presentations we're doing will address that in some future presentations. So, but for the moment, let's just accept that you've gone to this point, you've set up your GNSS receiver, and you're collecting some data. And what you get from that process is little h. Little h, which is your ellipsoid height, and it is defined relative to the most contemporary definition of the geometric datum, NAD 83, adjustment of 2011 in this particular case, as we are today. Now, the rest of it is big N, the geoid height or the geoid separation. The current geoid model used for the United States is called Geoid 12A or Geoid 12B. Geoid 12A and Geoid 12B are identical except in Puerto Rico. Right? B helped deal with a small problem in Puerto Rico. So if you're in the conterminous US, you have Geoid 12A, Geoid 12B, they're the same thing. And here's the equation. Big H, my height above the geoid, that's what I want, is equal to little h, right, my ellipsoid height, minus n. Now those of you out there who are watching this, if you haven't been asleep, you might ask, you might be sitting there saying, hey, why is that a negative number? Because this looks like it should be big H equals little h plus n. Well, the reason for the negative sign is that in the conterminous United States, Puerto Rico, and the Virgin Islands, the geoid is always below the reference ellipse. If you get up into Alaska, Hawaii, and the Pacific, it flips. It goes the other way. And the way NGS shows it is if the geoid is below the ellipse, then this number, big N, is a negative number. So minus a minus is a positive, okay? That comes up quite often in various presentations. So now the deal is, how well have I determined my ellipsoid or my GPS-derived height? Well, as I mentioned previously, the value for h that you're going to achieve is going to be a combination of the errors in the two elements. How well did you achieve the determination of little h? What are the conditions under which you made your GNSS observation? And then how accurately does NGS believe this value is? If you go to the NGS website and download the geoid model, or you go to an NGS data sheet for any one GPS-derived station in the network, they will show you this value to the nearest millimeter. On the data sheet, they are quite explicit that the fact that it's shown to the nearest millimeter does not mean it's good to the nearest millimeter. Both in the geoid model and on a link from the data sheet, you can actually use the NGS website to find out how good they think the data really is. And in most cases, you will see that NGS says the geoid height in whatever area you're in, most areas of the country, 95% confidence is generally speaking going to be somewhere in a range of 2 to 4 centimeters. So the fact that it shows on the data sheet or comes out in the model that you type in to the NGS toolkit, it comes out to the nearest millimeter, don't you believe it? Okay. And if you're capturing data from somebody else, make sure that they understand that as well. So the actual quality of the associated height is now dependent upon those elements. That being said, the process that the National Geodetic Survey has used to create the current range of geoid models is highly dependent on this procedure. Now, one of the things you'll see by the end of this particular presentation is how does NGS generate a geoid model? And I'm going to go through the data types that they use. But one of the most important things that NGS does is to create really what's referred to as a hybrid geoid. A hybrid meaning if I have a true geoid model, I'm using only gravity data. The hybrid says, well, the gravity data does not match my leveling data, and that's what I want. I want to be able to go anywhere, take my GNSS receiver, go out in the middle of a field, plop it down, punch a button, get a number, and make that number look like I did run levels to the nearby benchmark. That's what I want to do. That's the goal. And the way NGS has approached this up until only recently has been, all right, we know that the gravity data does not fit the leveling data at the couple of millimeters, even a few centimeter level. What do? Well, the procedure has been to acquire what they refer to as GPS on benchmark. That meaning, if my sketch shows an existing first or second order NAVD88 benchmark, or a benchmark defined in the datums of our island communities, Puerto Rico and the Virgin Islands, American Samoa, Guam, whatever they happen to be. If I go to a benchmark, I set up my GPS receiver and I collect data for some specific period of time. I can now determine little h. I've already described that. If I simply take that data and put it into the equation, I already know what big H is because NGS determined that as part of the first and second order leveling. I now have little h from my GNSS observation. I put them into the equation. It's going to tell me what n is at that point. So I'm getting an actual measurement of what we think the difference in that surface is at that point. And the more of those you do, the better NGS is able to model this relationship between the geoid and the ellipse. Every year in the spring, the National Society of Professional Surveyors, in collaboration with the National Geodetic Survey during Surveyors Week, encourages surveyors to go out and perform GPS measurements on existing benchmarks and submit that data through the service that they have that's referred to as Opus Shared Solutions. And so as a part of this presentation, we would highly recommend, the GNSS Users Group would highly recommend that wherever you are, if you have dual frequency GPS, that whenever you have a chance, go out and occupy those benchmarks. Submit that data to NGS as part of Opus Shared Solutions, and your data will help improve the geoid model in your community, in your backyard, next time NGS produces one of these types of models. And there may very well be at least one, if not two, between now and 2022 when NGS creates the new vertical datum. So that's a way in which surveyors and others, you don't have to be a surveyor. If you have a dual frequency receiver, you can still contribute. You don't have to be a surveyor. That users can contribute to the improvement in the geoid model framework. So let's look at the leveling, because this is the definition of the vertical datums. The earliest leveling that was conducted by the Coast and Geodetic Survey was along the Hudson River. Not a terribly long line, but these were the earliest days. NGS didn't even have their own levels. They had to acquire a level from Europe, and they struggled mightily with procedures and the process. The development of really a national vertical reference frame did not occur until the 1870s. At that time, the Coast and Geodetic Survey was already in the process of performing the transcontinental arc of triangulation, that is connecting the East Coast and the West Coast by the technique of triangulation, so we'd have a consistent horizontal datum. And at that time they made the decision that they were going to perform leveling along that same route, roughly along the same route, which was the 39th parallel. So beginning in October of 1877, they start leveling from the town of Hagerstown, Maryland, from a benchmark called A. It's still there today. If you happen to be in Hagerstown, Maryland for any particular reason, go to the courthouse and you'll find benchmark A. And they begin this process of leveling across the country. In 1881, they tied that leveling in to the National Tidal Reference System by connecting into what was then one of the longest term tide stations in the United States at the community of Sandy Hook, New Jersey. Now, notice here that epoch, 1876 to 1881, that's 5 years. 5 years. Those who work in tidal datums will tell you what you really want is a minimum of 18.6 years, what's referred to as a metonic cycle. Every 18.6 years, the Earth, the Sun, and the Moon repeat a particular dance about themselves, and you can model out the effects of large storms or other influences. So we're dealing with a fairly short time frame for tidal observations. But again, these were fairly new in the development of our reference frame. In addition, back then, the concept was that everywhere sea level is the same level surface. And today we know that is not. And you see the quote that I have here from the Coast and Geodetic Superintendent's Report of 1898-99, in which they said, oh yeah, we accept that mean sea level is the same everywhere. Well, today we know that is exactly not the case. Actually, the mean sea level appears to be about 1 meter higher, roughly about 1 meter higher on the west coast than it is on the east coast. So holding mean sea level as a definition is very, very problematic in trying to define a national vertical datum. I'm going to show you not only the different datums that we have, but I'm going to show you the extent that they started to cover the country. So here's just a list of the vertical datums that we either have had or currently have in the United States. So the very first, and they were often referred to as general adjustments. So the very first one came out in 1899, and was the second one in 1903, the third one in 1907, the fourth one in 1912. The one datum that many users in the country may be familiar with is the adjustment of 1929. And originally, in the very, very first, earliest publications, it was sometimes referred to as the fifth general adjustment, very shortly renamed thereafter as the sea level datum of 1929. Notice it does not say mean sea level. It says sea level because it was tied to tidal benchmarks on the East Coast, the West Coast, and the Gulf Coast of the United States, all as part of the leveling network. So it was not truly mean sea level, just sea level. That being said, it was often confused by many, many others as the mean sea level datum of 1929, as though, oh, now there is mean sea level in Des Moines, Iowa. No, there is no such thing, right? So that's something that if you're dealing with historic data, you do have to be aware of. The name was changed in 1973 to remove any confusion with mean sea level. So it was just simply renamed the National Geodetic Vertical Datum of 1929, NGVD 29, in 1973. Again, there was no change in heights whatsoever. It was simply a name change. The change in heights comes about from a reprocessing of all of the vertical data, all of the height differencing in the United States by the National Geodetic Survey, now as the North American Vertical Datum of 1988, and it was officially adopted in 1991, and it is the datum for the lower 48 and Alaska up till this point in time. The island communities, in most cases, had very, very poor leveling. So you're going to see here in this list, most of the vertical datums in the island communities are quite new. They're fairly contemporaneous. So unfortunately, you cannot level from Florida to Puerto Rico or from California to Hawaii. So each of them have to be on their own local vertical datums, and you see these are the most contemporary vertical datums in those communities. Hawaii is working on a leveling restructure literally as we speak. So the datums, the historical datums such as NGVD 29, for those of you who may either be in an island area or you may be working with data from an island area. And I've seen this many, many times, regrettably. Somebody will quote heights in Puerto Rico, for example, as being on NGVD 29. That never existed there. So users have to be very aware of the different types of datums, when they occurred, and their present conditions. Now I'm going to give you I'm going to run through quickly here just some slides that show you how the vertical datums expanded a little bit over time. And information about this does come up on occasion. So here we see the extent of the leveling across the United States by 1899. Now, regrettably, the National Geodetic Survey has never had a datum transformation tool that you can go to the toolkit and acquire that will allow you to transform heights from these older adjustments, the first, second, third, and fourth adjustment. All the datum transformation tool that they have called VertCon only goes between NGVD 29 and NAVD 88. So on those occasions when you may have legacy data, and this does come up from time to time, on one of these older systems, you actually have to go in and find some vertical control and produce these transformations basically by hand. So what I've done here in these slides is I've given you the URLs where you can actually find the description of that leveling, the adjustment of the leveling, and the associated heights and descriptions of the various benchmarks. So you can see by 1899, we're leveling out here towards about Denver, and we still haven't reached the West Coast. It also includes data from a number of different agencies, and realizing you can't read it very well on this screen, but you have the Army Corps of Engineers, and you have the railroads, and the U.S. Geological Survey all participating in this, providing at least what we now refer to as second order quality heights, and that data being provided to the Coast Survey for inclusion in the datum. By 1903, we're starting to see larger expansion in the Midwest, up into the Great Lakes area, certainly more data down into the Gulf Coast and into Texas. And then by 1907, we finally reached up into Sandy Hook, into Seattle. We've connected the East Coast and the West Coast. And then by 1912, we see further expansion down into the Southwest and a connection down to San Diego. So each one of these has their own adjustment, their own particular publication. And you will not find the heights for these marks on an NGS data sheet. Right? So if you have a benchmark that was part of, or you believe was part of, one of those older adjustments, those heights do not appear on the data sheet. You will have to go search them down from these publications. So let's highlight our most recent national vertical datum, NGVD 29. It's originally called the sea level datum 29. Its zero height, if you will, was fixed at 26 tide gauges. All of them had that full metonic cycle, 19 years. One of the problems was they didn't all have the same 19 years. Today, NOAA is very specific. All of the tide gauges are in the same tidal datum epoch. Back then, they had not defined a consistent tidal datum epoch for the United States. So again, it's not, as it says here, not truly a geoid-based datum. And here you see just a conceptualization of where those stations were located in the East Coast, West Coast, and Gulf Coast, and of course, with our neighbors in Canada as well. There was no NGVD 29 leveling in Mexico. A couple of slides that just highlight the expansion of the leveling network from about the late 1920s up till the 1950s. Leveling just went crazy across the country. Lots of leveling was being performed. It was very important to the national infrastructure. Particularly railroads were very big into this. So the Coast and Geodetic Survey worked with a number of different colleagues and components to improve this. By the late 1980s, it becomes important that we readjust this. And so here you see some of the differences, structural differences between the older datum NGVD 29 and NAVD 88. 26 tide gauges, 100,000 benchmarks, a little over 100,000 kilometers of leveling. When we move to NAVD 88, now we have a totally different process. Instead of holding sea level fixed at 26 gauges on each coast, NGS picks one tide gauge. One tide gauge. And I'm going to, in just a moment, I'll show it to you, I'll show you the area where it is, and I'll explain why. But notice that by 88, we have now nearly 500,000 benchmarks and well over 1 million kilometers of leveling. The idea being that this leveling, hopefully, will be a best fit for the geoid continentally. It turned out to be not quite that. So here you see the height differences. Height differences between NGVD 29 and NAVD 88. Notice the zero line running through here. Height differences smaller in the east coast, greater in the west. So the selection of one point, in this particular case, Father's Point, up here at the mouth of the St. Lawrence Seaway, that was selected for a couple of very specific reasons. One is that it's also the origin of what's referred to as the International Great Lakes Datum. So surveyors working in and around the Great Lakes, now NAVD 88 is essentially the same as IGLD. But probably more importantly, at a federal level, it minimized the height differences in the eastern part of the U.S. as opposed to the western part of the U.S., and that was as a request from the U.S. Geological Survey, because the topographic differences across the eastern U.S. on the USGS 7.5 minute topo maps are considerably smaller than they are in the west. So for example, had we selected Seattle as the origin point, which NGS could just as easily have done, it turns out virtually all the heights in Florida were going to be negative, and USGS wasn't having any part of that. So in a compromise, we picked Father's Point. It minimized the height differences in the eastern U.S., maximized them in the western U.S. But since the height differences were small, users have to be very, very well aware of what those height differences are and their datum differences. So NAVD8 comes along. I mentioned this. I highlighted these two issues as to why they were selected, right? And all of that was based on the use of leveling data. There was no GPS in the NAVD 88 like there was later in the horizontal datum. But now increasingly, of course, the use is, well, I want to use GPS. So that comes into play. I have to have a geoid model, and how good is it? I brought this slide earlier in the first presentation, but now I just want to repeat it. That the geoid, an equal potential surface to which gravity is normal and closely approximates mean sea level on a global basis across the whole Earth. Well, that's not what we have. So if that's not what we have, what is it we do have? Well, what NGS has are two types of geoid models. They start off with the best gravity data, and that's referred to purely as a gravimetric geoid. But it does not match NAVD 88. So to try and match NAVD 88, they compute a hybrid composite model, which includes the GPS on benchmarks that I mentioned previously. Let me show you the process by which NGS has gone through the compilation, the development of these composite or hybrid geoid models. So first we're going to look at, we're going to go back a little bit in time. We're going to look at Geoid 99, which consisted of about 6,200 GPS on benchmarks. And what I want you to notice, look real hard at where the densities of the little red dots are. Each one of those little red dots represents a GPS on benchmark somewhere in that community. So notice areas that have a few of them. A little bit of stuff here in Minnesota, and Maryland, and New Jersey, Florida, Harris-Galveston area. Other areas with not so much. Okay, so let's kind of sort of follow the bouncing ball, as they used to say in the old days. Right? Let's move forward now a few years in time from Geoid 99 to Geoid 03, and we're going to go from about 6,200 to down to 14,000 GPS on benchmarks. And look what's happening. Notice that the areas that were already doing GPS on benchmarks are still doing it. Minnesota, the Carolinas, Florida, Maryland, New Jersey, Vermont, little parts of Texas, like right around the Harris-Galveston area. Other areas, some modest amount of GPS on benchmark, but nothing like what you might see here in Minnesota. In Wisconsin, we see over here on the eastern side of the state the beginnings of height modernization, GPS on benchmarks. Let's move from geoid 03 now to geoid 09, 6 years, and go from 14,000 to 18,000 GPS on benchmarks. And what do you see? The same communities doing the same things. So the surveyors and institutions who are working in Minnesota and Wisconsin and Michigan and Florida and the Carolinas and Maryland, the geoid model is quite good there, but not so good in many other parts of the country for a variety of different reasons. There's a whole range of reasons why communities don't do the same thing. And what NGS has fully come to realize is that no matter what would continue to be done, the same things are going to continue in the same way. Now I'm going to show you now a map for geoid 12, the most current. The problem is that the team at NGS changed the format of the map, so it doesn't quite match the previous ones. And it actually looks like there's a lot of data, but it doesn't do it justice. But notice, again, mostly in the eastern U.S., less in the western U.S., but now, for the very first time, and I hope everybody can see this and notice it, these little red triangles, OPUS points, users who have submitted their data through OPUS shared solutions are now contributing to the improvement in the geoid model in their communities. So while the geoid model will continue to go this way until the new datums planned for 2022, when everything will go to a purely gravimetric model, until then, the best thing users out there can contribute is GPS on benchmarks in these various communities, and even filling in these holes in the eastern U.S. So very quickly, NGS produces a map that tells you how good it is. So you've got a color-coded map that tells you wherever you live, here's how good the quality of the geoid model is in your backyard. And let's understand, you cannot, that's why it's highlighted in red in big letters, big capital letters, you cannot currently achieve NAVD 88 or other island datum heights at national standards, the national standards being referred to as first, second, or third order. And I can't tell you how many times I have personally run into this where a surveyor says, oh, either I got second order or I want to go get second order or first order, and I want to use GNSS. You cannot and probably may never be able to achieve those levels of integrity with GNSS measurements. Maybe sometime way down the line, but certainly not anytime soon. So let me give you a very quick example. Here are the definitions for first, second, and third order as they are defined by the Federal Geodetic Control Subcommittee, which NGS has the chair. So for example, second order class 1 millimeter times the square root of k, meaning the distance between any two marks. Or second order class 2, I'm going to give you an example of second order class 2, 1.3 millimeters times the square root of k, which is, again, the distance between any two adjoining marks. So if you go out and run levels, can you achieve that? Yes. Is it easy? I wouldn't call it easy, but it's not all that hard either. Let's look at it from the perspective of GNSS. Let's just take an example. I want to achieve, or somebody tells me they got, second order class 2. Well, that's 1.3 millimeters times the square root of k, again, the square root of k being the distance between any two adjoining marks. And let's assume we have a line that's about 6 miles long. That means I'm allowed 1/100th of a foot, 95% confidence. What's the likelihood that you're going to achieve that with GPS? Never. Well, let's not say never. Not in the lifetime of anybody around, I suspect. It's just not going to happen. So if somebody comes to you and says, I need first, second, or third order heights, make sure you're ready to go, okay, gonna have to give you leveling. Or if you acquire some data from someone and they say, oh, these are second order heights or even third order heights, you should be going, time out, to run levels? Make sure you know the source of that data. So a couple of last examples before we finish up this session. Let me give you an example of 2 GPS sessions. What you see here are 2 sessions, and these were done as part of one of the high accuracy reference networks that NGS conducted. So you have these 2 points that are roughly about 11 kilometers apart. And they were observed on 2 days, 2 different days, right? Let's look at day 264, for example, from 2 o'clock down until 9 o'clock at night. That's a lot of data, 7 hours worth of data. That's a lot of GPS data. 2 different days, same amount of time. So if we processed, what we did is we processed all of this data. So you're looking at roughly 14, 15 hours worth of GPS data. And what we get out of that is the height difference, the ellipsoid height difference between those 2 points. In this case, it just happens to be minus 10.276 meters. And for purposes of this demonstration, that's being referred to as the truth, because it's highly unlikely you're going to find any much better than that with less than 16 hours, 17 hours worth of data. All right, so NGS grabs all this data, determines the height difference over that line. Then what they did, for purposes of this demonstration, is they went back and they took each one of those 2 sessions and they reprocessed each one of them as individual half-hour solutions. And they said, well, what do we get if we look at just half an hour's worth of data? And let's compare that. So in this particular case, see if I can do this. Here we have on day 264 a session from 8:30 to 9 o'clock at night. Here's the height difference from one 30-minute session. The same time frame, the second day. This is important. The same time frame, same time, same half hour. What are the height differences? Well, the 2 of them differ by 3 millimeters. Almost everybody go, wow, that's golden. I'm good to go. How does those 2 compare with the truth? 2.3 centimeters. Not bad. Not bad. Most people could live with that. That's quite good. Now, let's take that same process. Let's keep this one, but change the second session to a time in which we have a different constellation of satellites. At least 4 hours different. And that's what they've done. Now let's compare those 2. And what they've done over here, you compare the 2 of them, the difference between them has now gone from 3 millimeters to 4 centimeters. So right away you're going, whoa, wait a minute, oh, that went way up, that's big, that's a lot. Can I live with that? But look at how those 2, the average of those 2, compare with the truth. 1 millimeter. Now, we're not going to stand up here and say, oh, if you go do that, you're going to get a millimeter height. That's not the case. The deal is, if you need high quality heights from GNSS, one of the most important field conditions you can work under is 2 separate sessions differing by a minimum of 4 hours. So that you get a completely different or reasonably completely different constellation of satellites. That's one of the tricks you can use to get higher quality heights. So again, as I've pointed out in the previous sessions, difference about sharing or acquiring vertical data just as in horizontal. Understand, know the metadata. What datum are you on? What are the units of measurement? What is the accuracy? And again, the accuracy has nothing to do with the number of digits to the right of the decimal point. Let the user know how good the data really is. Again, some more examples of bad metadata. I do like to point out, in this particular case, we're talking about vertical. So here's one that was picked off a plat from a surveyor. It says top of the concrete bound. So right away that tells me that's probably somebody in New England, because they like to refer to their monuments as bounds. Elevation is 73.68 GPS datum. Well, all right, 73.68 what? Meters? Feet? Purchase chains, poles, rods, varas? Well, we know it's probably feet. The surveyor should say that. And what does he mean GPS datum? What is that? Is that an ellipsoid height? Left to my left brain geodesy would say, oh, GPS datum, that's an ellipsoid height, not an orthometric height. But you don't want to do that. Another example, and this we'll wrap it up on this. Here's another example, and it may be a little hard to see. This is a piece of a plat that a surveyor did, actually for an office that's part of NOAA, the National Oceanic and Atmospheric Administration. And they set out some monuments at a site in which you have people who are investigating conditions along an estuary. And they want to know how things change with time. So the surveyor set several monitoring points, monuments as monitoring points, and he provided to them the coordinates and the heights. Well, the first thing you see is the coordinates, northings and eastings. Well, what datum are they on, NAD 27 or NAD 83? And if they're on NAD 83, which realization of NAD 83? And are they state plane coordinates or UTM? What are they? You don't know. It's probably state plane, but the user shouldn't have to ask that question. It should be stated right on there. Okay, and what are the units of measure? Meters, feet, poles, chains. Washington happens to be a state that's defined as a U.S. survey foot, but you don't know that. So that should be defined. In the vertical, which of course is the discussion we're talking about here, the heights, the elevations, are shown as mean, MLLW, mean lower low water. Okay, that's the one piece of metadata that's on here. Mean lower low water. But which tidal datum epoch? I'm not told anything. And which tide station is it tied to? If I want to come back and match up these heights, or be able to have height differences and be able to account for them, I need to have that information. What is the tidal datum epoch? What tide station is it referred to? So metadata is so critical in our environment of high accuracy spatial data. We can talk about all these other things that have been talked about in the various presentations, but again, in many cases it comes down to the quality of the metadata that you are providing or whoever you're capturing data from is providing. So that ends this particular session on the vertical datums.